All right, hello everyone. Welcome to Physics 12 with Mr. Martin. Today we're going to be starting a new chapter. We're actually going to jump to chapter 5. We're going to skip chapter 4 for now. And looking at section 5.1 now. When we're in class together on the online sessions, we're going to be using the textbook more. But for these pre-recorded sessions, I will be using these notes. You also have a copy of these notes, a blank copy of these notes in your OneDrive as well, okay? So make sure to be utilizing those for yourself as you're taking notes and also looking at some of the practice problems we'll be doing together. So chapter 5 is all about rotational motion and some aspects of rotational motion that changes a little bit from regular motion or even two-dimensional motion that we've done in previous chapters, all right? So the first section, we're talking about centripetal acceleration and force as well. Since we can find acceleration, hopefully be able to also find force using Newton's laws. So here we will investigate the special case of kinematics and dynamics of objects in uniform circular motion. So first, let's consider a mass on a string being twirled in a horizontal circle at a constant speed. So you can imagine this, and I'm sure you've done this in your own kind of life as well, where you have an object on a string and it's just being, spun around, right? You have these, and maybe you're holding the string below and the object is just spinning around, okay? So let's see if we can determine the speed of the object, of this object in rotation, okay? Well, first off, we can remember that speed is defined as distance over time, okay? If we were looking for velocities, displacement over time, here we're just looking for for speed, so we're using distance over time. So let's see if we can figure out these variables. So, displacement, for distance, we can define the period of the motion. And so here, this will also kind of bring us to what we're doing in pre-calc 12 a little bit here, the period of a rotational object here, having this symbol t. And the definition of a period is the time it takes to complete one rotation, right? Or one full cycle, if you remember, for the sine and cosine functions. Okay, so the time it takes to complete one full cycle. So first, how far does it travel in one rotation? How would you solve how far the rock is traveling here, the object on this picture on the right? In one rotation, how far did it go? Well, the answer for that is it goes the circumference, right? It goes one circumference of the circle in one period. And can we find the circumference of a circle? Well, I would certainly hope so. Circumference is equal to 2 pi times the radius of the circle. And if we know the radius of the circle, we're able to solve for the circumference of the circle. And then therefore the speed of an object, so using this idea here, the distance that the object travels is 2 pi r, okay? And the time component would be the period for which it travels that distance, okay, for one rotation. So this would be our formula for speed here, okay? This is not just time on the bottom, it's capital T, which represents period. All right. Okay, so we figured out its speed, but is the mass accelerating? Here, when you're rotating this object, is there an acceleration happening on this mass? Do you have to apply a constant force here in order for the object to continue rotating around? So the answer here, we know that acceleration is equal to change in velocity over time. So we have to figure, okay, so we know that the speed can be constant because it tells us in the original question here that it's constant speed. But can we say that the rock or the object has a constant velocity? The magnitude of its motion is staying the same, but is the direction of the rock staying constant? The obvious answer is no. So because there's a change in direction of the rock, then there must be an acceleration to cause that change in direction. Okay, so the answer is acceleration definitely is happening because the velocity, even though the magnitude of the velocity is not changing, the direction of the velocity is changing. Okay, and so you can kind of visualize this like this. And so here, if the rock is at the top of the circle, at that very moment, its velocity is straight out. Okay. However, at the side here, the velocity of the rock would be actually going straight south. All right. And at the very bottom here, the velocity of the rock, the velocity is always going to be tangent to the circle where at the position it is on the circle. Right. So those lines that I drew, these are all lines that are tangent to the surface of the circle at that exact point. And you can put lines in between each of these, of course, and they would just be more tangent lines. And so here we have acceleration happening because we have change in velocity, right? Velocity 1 and velocity 2 are in two different directions. So there's a change in velocity, and that change in velocity happens over time, right? The time it takes for the rock to get from the position 1 to position 2, right? So we have a change in velocity over time, therefore we have an acceleration. And the acceleration happens perpendicular to the tangent line towards the center of the circle. But what direction is the acceleration happening? Is it outwards or inwards? Now, this question oftentimes confuses students because we've maybe all been at a fair, and you enter that fair ride where it just spins around in circles, and you're kind of stuck against the outside wall, and it kind of lifts you up at the same time, and it makes you dizzy. So here you're experiencing what feels to be an outward force. Okay. It feels like your chest is being pressed on, and so you feel like you're accelerating outwards. But what is actually happening is that you're actually accelerating towards the middle of the circle in those experiences. And we'll talk more about why that is, okay? So this is acceleration of a rotating object, what we call centripetal acceleration, which is acceleration seeking the center of the circle. That's literally what it means. So there is an acceleration here because even though you have a constant speed, your velocity is changing directions, and we have that, and that acceleration that is towards the inside of the circle. Okay. Now notice here that the direction of the velocity at any time is, here we kind of demonstrated this already, but we'll write it down. It is tangent to the circle. It's tangent to the circle, okay? That's what I was showing you guys here by highlighting this vector over here, okay? And each of these vectors that I drew for velocity, whether it be velocity 1, velocity 2, velocity 3, velocity 4, velocity 5, okay? All of these vectors are drawn tangent to the surface of the circle, okay? And that's how we assume. Just because if you were to break the circle and just let go of the rock, it would fly off tangent to where it was released straight ahead. Okay, it would stop rotating, it would fly forward. Okay? So, even though it may be traveling at a constant speed, anything traveling in a circular path is accelerating because the direction of its velocity is always changing. All right? So, how do we calculate this acceleration? Well, there's two formulas we can come up with. Okay, the first one is v squared over r. So if you want to find centripetal acceleration, v squared over r. And the second equation is 4 pi squared r over period square. Okay? Now, the equation that you're going to use just depends on the variables that you're given in the question. If you're given radius and period, then you want to use the second equation. If you're given velocity and radius, you want to use the first equation. Okay? And one is just derived from the other. Essentially what we've done here is for the first equation, which is v squared over r, if you substitute the formula that we came up with for velocity at the top here into the position of v, 2 pi r over t squared over r. Okay, once everything is simplified here, so one of the r's is going to cancel out the squared. The 2, this exponent is going to be applied to the 2 to give you 4. It's going to be applied to the pi to give you oh, that's a lot of legs on that pi. Pi squared. Here it's going to be applied to the r, which would make it r squared. But then you have an r at the bottom here that cancels out one of the r's at the top. And so you're just left with an r without the squared. And then that leaves you with the exponent 2 being applied to period in the denominator. And so that's how we end up with that equation. Okay, so it's just using the formula we came up with for velocity and applying it and substituting it for the v in our first equation for acceleration, centripetal acceleration. All right. Now you may be wondering, okay, that second equation makes sense from the first equation, but the first equation doesn't make sense. So we're going to do a quick just kind of demonstration as to why the first equation works. Okay, so I'm going to start off by drawing a circle. Okay, don't judge my circles. And so here, the center of the circle, right, if we have a rock at 2 points, okay, the rock in both points is radius away from the center of the circle. Okay. However, the velocity at the first position is, tangent to the circle at this position, and it's also tangent to the circle at this position here. Okay. Now this position here, so R1 and R2, and then we have essentially what is a change in R, change in radius in terms of direction, not necessarily magnitude. Same thing with velocity, right? The magnitude of the velocity isn't changing, but the direction of the velocity is changing. So we can come up with a change in velocity as well, okay? And this change in radius is the closer and closer you take 2 points, that change in radius is becoming closer and closer to the side length of that arc length of the circle, right? So for example, if you take 2 points that are wide apart, like here and here, yeah, okay, so the change in radius here is not very similar to the arc length between those 2 points, right? Because that big curve is kind of throws everything for a loop, okay? However, if I were to do the same object at 2 different points, but make those 2 points very close to each other, right? Now all of a sudden that change in R is getting closer and closer to that arc length. Okay, to essentially, and the closer you get to, the closer the 2 points become, the more equal those two values become. Okay, so essentially, as you're moving closer to 0 in the difference between the positions, or time if you want, the more the change in the radius is equal to the arc length of the outside of the circle. And so that's the assumption that we're making there. Okay. All right, so a couple things that we want to do. First of all, the magnitude of the velocity 1 and 2 are going to be the same. Okay. However, because there's a change in direction, we do have a change in velocity, right? And change in velocity is, of course, velocity final, velocity 2 minus velocity 1. Or we can rewrite it as velocity 2 plus negative velocity 1, right? When we're, let me give velocity 1, not velocity initial, when we're wanting to add vectors. So here, my velocity 1, or my velocity 2, I'll try to recreate it over here with the same shake and everything. Velocity 2 looks something like that. Okay, and velocity 1, now I want to put the negative of velocity 1. So velocity 1 is this is negative v1. And so that negative v1 is going to be, something like that. Okay, v1. So your change in velocity looks something like this. Change in velocity. Now you might be saying that change of velocity doesn't look like it's heading towards the center of the circle between those 2 points. And you'd be right. However, again, just like for the arc length and the change in radius that we looked at on the red line on the circle, the closer the 2 points you take along the rotational outside of the circle, the more the change in velocity is going to point to the center of the circle until the 2 points are so close together that it points directly to the center of the circle. So for all intents and purposes, you can assume that change in velocity, if the points are close enough together, is pointing at an instantaneous change in velocity towards the center of the circle, even if it doesn't point that way if you were to take 2 points that are far apart. Okay? All right, so now that we're able to see our change in velocity, we're going to be able to use this to create a ratio. And so the ratio that we're able to create is the change in velocity. If you were to take the change in velocity over the magnitude of your velocity, it would equal to the change in radius, or arc length there, taking an instantaneous value over your magnitude of your radius. Okay, and if we were to combine that with our equation of, okay, so if we take this formula here, we can come up with a formula that can solve for a change in velocity, right? If you cross multiply, you end up with change of velocity is equal to velocity, magnitude of velocity times change in radius over radius. Okay, this is a v. And if we combine that with our formula that we had originally, which is for velocity, a regular formula for velocity, which is a is equal to change in velocity over time. Okay, we can substitute these variables in the place of delta v. And so a is equal to, I'm going to substitute in red, v times delta r divided by r. Of course, this is still times time. Now, if I take these two variables here, the change in radius over the time it takes between the 2 points on your circle, that's also going to equal to velocity, right? Because you have a distance, which is the change in that arc length or radius, and we said the closer the 2 points get, the more the change in radius is equal to that change in arc length. And divided by time, that's going to give me another value for velocity. So now I have velocity twice. I'm going to substitute v in the place of delta r over t. And I end up with the equation of A is equal to V times V divided by R, or V squared divided by R. Okay, so that's how we end up with the equation that we have here. Okay. Couple things worth noting here from the above derivation, that the direction of the change in velocity is always assumed to be towards the center of the circle. Okay, because we're using the points that are closest together because we're looking for instantaneous acceleration. So we're trying to find 2 points that are separate but so close together that we gives us a good picture at that point where the change in velocity is headed. Okay, therefore the acceleration of an object in a circular motion is always towards the center also. Okay, this is the definition of centripetal accelerate or motion in general, is center seeking. So it goes towards the center. Okay, we'll be looking at that a little bit more later on. So continuing on here, whenever an object is accelerating, there must be so whenever there's an acceleration, there's a net force, right? Newton's second law, which is force, specifically force net, is equal to mass times acceleration. And so this force, if the acceleration towards the center of the circle is called centripetal acceleration, the force that causes centripetal acceleration is going to be called centripetal force, or F subscript C. It's not a new force, it's simply the net force that accelerates an object towards the center of the circle. This force can come in different shapes or forms. So for example, when a mass is twirling in a circle at the end of a string, like in our example, our centripetal force is provided by what? What type of force is that actually? Here, that because it's a force applied by a string or a cable, it is a tension force. Okay, so we see that centripetal force is just the rotational application of a force we already know, which is in this case tension force. When a car rounds a corner on a highway, the centripetal force is provided by force friction, right? Friction on the tires, and the kinetic, the mu, coefficient of kinetic friction between the tires and the road is what's going to provide the centripetal force and give that rotational. Okay, and last one here, when the moon is orbiting around the Earth, that's gravitational. Gravitational force. Okay, so again, none of these centripetal force, none of these examples are a unique force. It's just the using of a force that we know already in a rotational kind of context. Okay, so using Newton's second law, that can help us determine a formula for centripetal force, right? And so we know that centripetal acceleration is equal to v squared over r. We also know that it's equal to 4 pi squared r over t squared, right? Those were their two formulas. Okay, now if we want to find force centripetal, all right, well, force centripetal is caused by centripetal acceleration times mass. Okay, so essentially the only thing that these equations for centripetal acceleration is missing is a mass component in the front. Okay, and once you add those m's, you have formulas for your centripetal force and not just your centripetal acceleration. So let's look at some of these forces in action. So first question, a 0.5 kilogram mass sits on a frictionless table and is attached to a hanging weight. the 0.5 kilogram mass is whirled in a circle of radius 0.2 meters at 2.3 meters per second. Calculate the centripetal force acting on the mass. All right, so we're going to start with a free body diagram here. All right, we have the object. It's sitting on the surface of the table, okay? But it's attached to a hanging mass. Presumably, maybe there's a pulley here for the hanging mass to be attached to. And then we have the hanging mass here. Okay, what are the forces involved here? Because there's a surface, we have force normal, we have force gravity, and we have force tension. Down here we also have force tension. And of course we have, this force tension is going upwards, and then we have force gravity. Why didn't I draw a centripetal force? Why doesn't centripetal force show up here? Because we know that the option is rotating. What's causing the rotational motion here? Well, the answer to that would be the force centripetal here is coming from the force tension. Okay, so that's why it's not a unique force in my diagram. However, I do know that that force centripetal is being caused by the tension in the rope because of the weight that's hanging down. So the centripetal here, I have mass of the object, the velocity squared, and the radius. Those are the variables that I have, right? I have radius, I have velocity, I have mass. So this is the formula I want to use. If I had period and radius, I would use the other formula. So I'm going to substitute these values in. 0.50 kilograms, and then a velocity of 2.3 meters per second. That's going to be squared, and then divided by 0.20. All right, and then I just plug and chug here. I end up with an answer of, in my calculator, 0.5 times 2.3 squared, and that's going to be divided by 0.2. And I end up with my answer in this situation. This question only has 2 sig figs, so I want to just keep 2 sig figs. So this would be 13 newtons. Because we're dealing with force, of course, our answer is in newtons. All right. So in this situation here, we want to know, calculate the mass of the hanging weight. So we want to know, what is the mass of this object here? Okay. We know force centripetal in the system, force centripetal, and we know that that is equal to force tension, okay, because it's the force tension that's causing the centripetal force. All right. Now, if you just take this portion of the diagram, you'll also see that there's only two forces acting on this mass, and because the mass is not moving up or down, it's in equilibrium, those force tension has to be equal to force gravity. So what we've determined here is then our centripetal force is equal to our force gravity, okay, because they're both equal to the tension force. So therefore, because I know that force gravity is equal to mass times acceleration due to gravity, here I can substitute centripetal force for gravitational force because they're equal to each other. And if I'm looking for mass, and then I can substitute 9.81 acceleration due to gravity there. Okay, so this is 13 newtons is equal to mass times 9.81 meters per second squared. Simple algebra here, divide both sides by 9.81, and I end up with a mass of 13 divided by 9.81. Again, just 2 sig figs of 1.3 kg. Awesome. Let's look at another example. This example here, a red Tiburon. I actually owned a red Tiburon once. It was a fun little car, but I sold it. So a red Tiburon here traveling at 14 meters per second goes around an unbanked curve. Okay, we'll be dealing with questions with banked curves later on, but unbanked curve, that means there's no angle to the turn. In the road that has a radius of 96 meters, what is the centripetal acceleration? All right, so here I'm looking for AC, right? I have those two formulas. Which formula should I use? Should I use the v squared divided by r, or should I use the 4 pi square r divided by period squared? Well, here, because I have velocity given to me at 14 meters per second, and I have a radius, which is 96 meters, I should definitely use the first equation. I plug those numbers in, so 14 squared divided by 96, and that's going to give me my centripetal acceleration. So 14 squared divided by 96. Oop, that's a 396. Then again, here I have two sig figs. It'd be 2.0 meters per second squared. And that would be towards the center of the circle. Okay. Now here, they want to know, okay, so that's your acceleration. What is the minimum coefficient of friction between the road and the car's tires? Okay. So here, the force, in order for the force friction, so what is causing the centripetal force in this situation is the force friction. Okay. So here, force centripetal is equal to force friction. Okay. And then here I know that force centripetal is equal to mass times centripetal acceleration. And force friction is equal to mu times force normal. Okay, and instead of writing force normal, I'm going to be times mass times 9.81, right? Force normal in this situation is just equal to force gravity, which is mass times the acceleration due to gravity. And so once I've had these variables here, I see that I don't have the mass of the Tiburon, but once I write it out like this, I can see that the masses actually cancel out. So that leaves me with an equation of centripetal acceleration is equal to mu times 9.81. I know that my centripetal acceleration is equal to 2.0. I solved that in the previous question. So that's equal to mu times 9.81. And again, simple algebra to solve for the mu, the coefficient of kinetic friction. So I do 2.0 divided by 9.81. And I get a mu, 2 sig figs of 0.20. All right. So those are those two questions. One last example here of a plane making a complete circle with a radius of 3,622 meters. And it does so in a time of 2.1 minutes. Okay, so here, and that's the time for the complete circle. So that's not just time, right? The time that they give us here is not just regular time, it's period, because that's the time for one full revolution. Okay, now we have to convert our minutes into seconds, right? We don't want, it's in seconds, not in minutes. And so do that, 2.10 minutes, and dimensional analysis, then 1 minute, you have 60 seconds, and that's going to give you 126 seconds. All right, so 126 seconds. And here, what is the speed of the plane? Okay, so they're not asking for acceleration, centripetal acceleration or centripetal force. They're just asking for the speed of the plane. And we saw at the beginning of these notes that the speed of the plane is equal to the circumference of the circle that the plane traveled divided by the period, the time it takes to travel that circumference. And so here I'm just plugging in values. 2 pi times the radius, which is 3,622 meters, divided by 126 seconds. Okay, so if I can plug this into my calculator, and I want an answer to 3 sig figs. So this would be 2 pi 3622 divided by 126, and I get an answer of 181 meters per second. That would be the speed of the plane. Okay, no, they're not asking for magnitude. They're they're not asking for velocity, just speed. One last note here is a little thing called centrifugal force. You may have heard of. While centripetal force means center seeking, which we already saw earlier in our notes, the word centrifugal means center fleeing. Okay, so this is the idea that the force is actually working outwards instead of inwards in a circle of an object that's being spun or in rotational motion. The reason why people think of this concept of centrifugal force exists is because the experience tells you that it feels like you're accelerating outwards. If you've ever been on that ride that I was describing before, you feel like you're being accelerating outwards because your chest is being pushed down. But that's not actually what's happening. You're not actually being accelerated outwards. So here in our notes, it explains it to us a little bit. An inertial frame of reference is one where Newton's laws are true. Okay, so we're assuming that's a good starting assumption. In an inertial frame of reference, centrifugal force is actually an apparent force. Okay, it appears that there's a force, but it's not. It does not actually exist. So what are you feeling then? If it's not centrifugal force, it is simply the apparent force that causes a revolving or rotating object to move in a straight line. However, Newton's first law tells us that we do not need a force to keep an object moving in a straight line. You only need a force to deflect an object from moving in a straight line. So here, essentially, what is causing you to feel like you're flying outwards or backwards is actually your inertia, not some force. Okay, so if I were to draw that circle, imagine you're on the wall here. Your body, if you're spinning around, your body wants to continue going this direction, but the wall of the ride pushes you towards the middle of the circle, preventing you to fly outwards with your inertia. Okay, and that wall, if you think about it, that's a normal force pushing towards the center of the circle and opposing the inertia. Okay, so what people call centrifugal force is actually just inertia working to keep you moving in the direction you were going. And it's centripetal force that is towards the center of the rotational motion that is changing your velocity. Okay, so that's kind of where the misconception come from. And an example of this is when you're riding in the back seat of a car that is turning. I'm sure you guys have been in this situation before. You slide across the seat, seeming to accelerate outwards away from the center of the turning circle. When you turn left in a car, you feel like your body is being accelerated towards the right. Okay, that's why that joke comes from. I think I've shared with you guys about left turn dates and right turn dates with bucket seats. If the date didn't go well, you want to be turning left all the way home to have the person slide away from you as much as possible in your car. of course, without falling out. Whereas if the date went really well, maybe you plan more right-hand turns on the way home so that the person next to you, slides closer to you. Anyways, that's the left turn dates and the right turns dates jokes. So in this situation here, explain why the force in this case is actually working towards the center and not outwards. So if you take this left-hand turn, okay, so you're in a car and you turn this corner, all right, your body, once you're like here, your body wants to keep doing what it's doing. Right here, it wants to keep moving forward. So here, it wants to keep moving forward again as well. But it's actually the wall, the side of the car and your seatbelt that is forcing that direction to change along with the car. Okay, and the direction of that change is towards the center of the curve that you're turning around. Okay, so because of Newton's first law of inertia, your body wants to keep moving in a straight line. Okay, it is the inertia that you feel that is mistaken for a force pulling you outward. Okay, it's just the inertia. It's not actually a force. In reality, it's the seatbelt, the friction, and the door of the car that's actually pulling you in towards the center of, and it's not really pulling you, it's actually pushing you in towards the center of the circle that you're traveling. Okay, so that's kind of an explanation there. Hopefully these notes were helpful, and I'll be giving you guys your homework assignment during our next class, also posting it on Teams.